Hello, physics class, and welcome to problem set 36, day 1. Getting ready for the last test of the year, so I hope you're ready for a great day today. So, in this concept, as we do another electricity lesson, it says a 24-volt ideal battery is connected to a 48-ohm resistor. How much current flows in the circuit? How much power does the battery provide? And how much work is done by the circuit in 3 minutes? Okay. Anyways, as we have this, we see that we have 24 volts heading through a 48 ohm resistor. And the first thing it asks for is the current. You should remember from a couple lessons ago that V equals IR. Do you remember what that stands for? You're absolutely right. It stands for volts equals amps times ohms. Okay? So in this particular case, we have a 24 volt resistor and a 28 volts power source and a 48 ohm resistor, and we'll need to calculate I, or the number of amps. So take out our handy dandy calculator. Probably you don't need to. You can probably see what this is going to be, and we're going to take 24 and divide it by 48. And if you said, yeah, Mr. Wilson, the amps is going to be half an amp, 0.5 amps. Now, the next part of the question is where we get to the new lesson. How much power does the battery provide? Well, we need a new equation. And the new equation that we're going to have here is that P equals V times I, or power equals volts times amps. All right, power equals volts times amps. Now, as we move forward, I'd like you to think, if V equals IR and P equals VI, could we make I'm going to write down a new word here. Could we make a corollary of that equation? If V equals IR and P equals, that's not R, that's P equals VI, couldn't we take this and substitute it into volts? Or maybe we could solve for I in terms of R and get another equation here. Well, if I plugged in V into IR, we'd get P equals I times R times I, or I squared R. So that's a corollary. That's another way you could solve this, like if we didn't know the number of volts. However, in this problem, we actually do know the number of volts. So we're going to say power equals 24 volts times the 0.5 amps. So the power level, if we were to take our 0.5 and multiply by 24, we'd get 12. And what's the unit for power? We should know this from physics class already this year. You're right, 12 watts. So that's the amount of power that we have coming from the system. And then it says how much work is done by the circuit in 3 minutes. Well, then we just kind of get a unit analysis. What is a watt? Well, a watt is equal to a joule per second. A joule per second. So this would be 12 joules happening every second. And in 3 minutes, every 1 minute is 60 seconds. So 3 minutes is 180 seconds. So if we put this into our unit analysis over here, 180 seconds. Seconds will cancel. The only thing left is joules. So 12 times 180 gives us a grand total of 2,160 joules. That makes it answer time. We have in the question a total of 2 significant digits, so our solutions will have 2 significant digits. For part A, I equals 0.50 amps. For part B, P equals 12 watts. And for part C, the work is 2,200 joules. Okay, new concept, not too hard. Hopefully you grab the concept and it can be something we can pass on to the end of the year, which is coming up here. I can't believe I haven't seen you guys in class in weeks and weeks and weeks. It just feels so strange. Okay, now similar type of question. It says here that we have 4 amps. Ooh, not volts. 4.0 amps. And this should say a 20 ohm resistor. I'm going to have to go back and fix that. So this is a 20 ohm resistor. So V equals IR. And we know that amps is 4 and the ohms is 20. That will give us the volts. 4 times 20 equals 80 volts. Then it says find the power output of the voltage sources. Well, we just said P equals, what did we just say? Volts times amps. In the last slide, we said volts times amps. Or we could say also I squared R. Now, because in the question, we knew that there were 4 amps and the resistor was 20 ohms, in this case, I could use that instead of going back to we should get the same answer either way. So we'll get 4 squared is 16 times 20 is 320 watts. Let's just say we did that the other way. We said P equals V times I. We calculated 80 volts and 4, and we had 4 amps. So we had 320 watts. Now, as we move forward, I'd like you to think about, and I really want you to process, if this is a corollary of power equals volts times amps, can you come up with another corollary of the same with using the same method and come up with a different way to solve the amount of power put out by the system? I hope so. We have 2 significant digits in the question, so we're going to say that for A, V equals 80 volts, and for B, P equals 320 watts. Okay, let's move on to the next question. The next question, it says, our observer here from 3.62 kilometers hears a horn, and they hear the horn of the sound 10.5 seconds later. What is the speed of sound in the air that day? I've given you enough information to be able to do a problem like this, but let's just say that we have an air horn. And it comes out here, and the sound comes out. We have an observer over here, not an 8, an observer. Let me just start over. We have an air horn. And the air horn lets out its sound. We have an observer, and he waits, the horn fires, and 10.5 seconds later, he hears the sound. The sound hits his ears, and he is 3.62 kilometers away. Well, speed of sound is calculated in what units? We've talked about this in last week as we were working on sound. We said average speed of sound in air is about 350 meters per second. Well, we learned already in this particular problem that he is 3.62 kilometers And we'd want it in meters per second. So we know 1 kilometer is equal to 1,000 meters, and it takes 10.5 seconds. So using just basic unit analysis, kilometers will cancel, and we're left with meters per second, which is the unit that I'd like to have in my sound, and to compare it to the average temperature, average speed of sound on a nice clear day. So 3,620 divided by 10.5 is a grand total of 344.76 meters per second. Very close to the average, but a little bit slower on that day. Probably a little bit colder would make that be the case. So 3 significant digits, we'd say 345 meters per second is the speed of sound. This is something that would make this is something you could do in a lab by yourself. You could say, all right, I want to calculate the speed of sound. So, but you'd have to be listening to something that you'd have to be like a mile away or something like that. But this is something that you could do, especially if you can hear a train from your house and you know approximately the distance from your house to where the train is blowing its whistle. You could calculate the speed of sound on that day. All right? Okay, so here's another question that we're going to face in the homework this week. It's one we've kind of been working on, but we're looking at it from a little bit different perspective. And this is buoyancy force problem with Archimedes' principle. So it says a sailboat is floating in the water. The total volume of the boat is 41 meters cubed. And 55% of the volume is submerged. Find the mass of the water that is displaced by the boat and calculate the buoyant force of water. Find the weight of the mass of the boat. All right. So the buoyant force is able to hold this up. That's going to be very, very important. Archimedes' principle says buoyant force is equal to the weight of the mass of the water that is displaced. So what we're going to do is we're going to first start talking about the volume of the boat. The total volume of the boat is 41 cubic meters. So what would the submerged part of the boat be? Well, if it says it's 55%, what I'm going to do is I'm going to take 41 and multiply by 0.55, and then it'll be meters cubed. So the volume of the submerged part is going to be 41 times 0.55 to be 55%, and I get a grand total of 22.55. That's the amount that's submerged. So what I'd like to do is I'd like to find the weight of the water that's displaced. So let's see if we can do that. Let's start with the density of water, which is 1,000 kilograms per meter cubed. And let's multiply by our 22.55 cubic meters. And if I did that, I took 22.55, and all I really have to do is move the decimal place a couple of times. We're going to get 22,550 kilograms. So I'd say that that's a unit of mass that's then displaced here. Now, if I took again and if I said, okay, 1 kilogram is equivalent to 9.81 newtons. So if I took it and I just multiplied by 9.81, I am going to get the buoyant force of 221,215.5 newtons. Now, if I were looking here, how much is pushing up? 221,215.5. Now, is this accelerating? No, I'd say it's in a state of equilibrium. So the force normal that's going to be pushing down is going to be the same as the buoyant force that's pushing back up. So that would also be 221,215.5 newtons. Because if it was any heavier, it would sink a little bit more. If it was any lighter, the water would push it up more. So the weight of the boat is the same as the buoyant force, 221,215.5 215.5. These are equal, and I tried to illustrate that in the diagram. That would also make the mass of the water displaced and the mass of the boat the same. I've seen labs where what they do is they will calculate the weight of an object that floats, and they will put it in something where the water level is just the same as the brim of a spout. And then they'll put that in there, and then they will measure the weight of the mass of the water displaced with the mass of the block, and they are fairly equivalent within a percentage of observer error. So, but this is a true principle here that works. So, if I were to come up with my answers, I'm going to get that. Let me get a different color here so we know these are the answers. A, the mass of the water that's displaced by the boat. If I got 3 significant digits, I know that there's a percentage of 55%, but like with angles and 55%, we're just going to kind of play those out. Let's let these actual measured values be the significant part. So we get 22,600 kilograms. B, the buoyant force, is 221,000 newtons, and C is 221,000 newtons because the weight of the boat is the same as the buoyant force, and D, 22,600 kilograms. So if I found the mass of the water that's moving out of the way, it should be the same. All right. Well, I hope that you learned something today, that we learned some new concepts, and we're getting near the end. Again, my plan is that we're going to have a test on Friday, and then next week I'm going to be giving you the final exam, not as an exam, but as a final homework problem. Thank you for listening. Thank you for being patient. Hope you're looking forward to the